Assalamualaikum and hi to everyone. Thank you for watching this video. So in this video, we continue on the second part of the process synchronization. On the last video, we already talked about the lock, the mutex locks, the process how we lock on certain process, then we allow the other process to be executed. And then we also talk about the deadlock, the starvation, and the small fall. So in this video, we continue on another part on the classical issues problem in the synchronization. So basically, we just continue on the previous part, still under the topic of process synchronization in our operating system. Okay, so the last video, we learned about the critical section problem. Okay, when we talk about the critical section problem, it must try to solve the three part of the problem. Okay, must at least solve one of the three part of the criteria. And then we have the synchronization hardware. We learn about the hardware, and then we learn about the semaphore, the variable that we use. And the monitoring process. We also talk about the lock part, the mutex locks. And so now at the second part, we will learn and discuss about the classic problem of the synchronization. So basically under this topic, you should know what is the synchronization, what is the synchronization, why this synchronization is very important. Why? Because when we talk about the multi-processes in our operating system, so this synchronization is very important because we have the same data set, we have the same data, that data is available to be shared among several processes. So that means we have a lot of processes that try to access to the same data. That's why the synchronization is very important. So under this video, we'll talk about the classic problem of the synchronization. So basically, here we use these test newly proposed synchronization schemes. Here we have bounded buffer problem, readers and writers problem, dining philosophers problem. So we will go one by one. Okay, the first part we go for bounded buffer problem. So basically under the bounded buffer problem, we have the n buffers and each can hold only one item. Okay, you need to recall what is the semaphore from the previous video. So the semaphore mutex initialized to the value 1. Okay, it's just like when we do the logically on the programming part. So we assign the initial value for the semaphore mutex is equal to 1. And then we have another part, semaphore full, we initialize as value 0, and semaphore empty initialize to the value of n. So we have 1, 0, and n. So these are the structure of the bounded buffer problem. So we have two parts. We have the producer and we also have the consumer. So this is the first part which refer to the producer. We assume that these are the structure for the producer process. Okay, we do something and produce an item in the next produce. So means the producer will produce something. So we call the function with. Okay, and when you call the function with at the first, empty is referred to this part. Okay, the initial value for the semaphore is equal to the n. And then wait for mutex equal to 1. And then add next produce to the buffer. You're waiting for the signal for the mutex and the signal for the full. Okay, while true. So this part for the producer part, and this one for the consumer process. So at the consumer process, they need to wait for full, wait for the mutex. So remove an item from the buffer to the next consume. And then we have the signal mutex and signal empty, and then consume the item in the next consume. So we have two part, producer and the consumer. So in this bounded buffer, we need to consider that the buffer which can store n items. Because at the first part, we talked about the n buffers and each can hold one item. So a buffer which can store n item, and a producer process which create the item one at time. Means at one time, the producer will process or create one items, and a consumer process the item that produced by the producer, so one at a time. So a producer cannot produce unless there is an empty buffer slot to be filled up, to be filled in. So it need to wait until there is empty buffer, then it can fill in. And a consumer cannot consume unless there is at least one produced item. And when the producer produce the item, then consumer only can process it. So these are the logic. At the small for empty equal to n. So full equal to 0, mutex equal to 1, and then process at the producer part while true. Okay, empty acquire, mutex acquire. Okay, this one is refer back to this assumption. Okay, assumption as this value. Mutex initialize as 1, full 0, empty, and value. So empty and full 0, mutex 1. Okay, and then at this part produce mutex dot release. Okay, full dot release, then process consumer. Okay, after it produce, then consumer can process. So this part under the bounded buffer problem. So this is the diagram. Okay, we have two part, the producer part and the consumer part. Then we have two pool. Okay, pool. Ada kolam kat sini. So one for empty pool and another one for full pool. Okay. So the problem here we call as the producer and the consumer's problem. A finite supply of containers is available. So producer take an empty container. Okay, producer take the empty container and fill it with a product. It is analogy, or you can try to imagine about the producer and the consumer's part. So when there's an empty container, then the producer can take the empty container and fill it with the product. Otherwise, it cannot put their product. And at the consumer part, it will take a full container and consume the product and leave an empty container. So basically, the main complexity of this problem is we must maintain the count of both for the producer as well as for the consumer. Means we need to know the number of the empty container and the full container available, the availability of the container. Then we can process. Okay, the next part is about the readers and writers problem. Okay. Why the readers and writers problem? Okay, first you need to know what is the readers and what is the writers. Readers is we can assume that when we have the data that being shared, let's say in our library we have multiple books. Okay, the books is referred to the data. And then we have the borrowers or the readers, which are the student and lecturers and staff, academic staff or non-academic staff that able to reach to the library, take the book and read it. Okay. So the same things happen in our operating system where we have the data there, okay, and we have multiple users. We have multiple process, okay, because of the multiples that can access the same data. So this might be a problem. Means the readers and writer might be a problem. Basically, if you try to imagine, when we have books at the libraries, anyone can read it. There should be not a problem. But when someone want to update the books, and while in the same time someone want to read, it might be the problem. So that's the analogy of the readers and writer is about we have the data. People may view the data, but how about when they want to view the data, but the data need to be updated? In the process of updated, it might be a problem. So a data set is shared among a number of concurrent processes. Okay, we have multiple there processes. So readers only read the data set. Okay, they do not update the data. They do not do anything. They just read the data. Writers can both read and write. So we have two roles here, readers and writers. We want to allow multiple readers to read at the same time. This might be the problem because we only have limited data. So multiple readers is allowed to read it. Okay, only one single writer can access the shared data at the same time. So we have the problem. We have multiple readers and we have writers. And writers want to update the data. So several variations of how readers and writers consider all involve some form of priority. Okay, so we have the shared data is referred to the data set, and then we have the semaphore read write mutex. So this one is initialized to 1, and semaphore mutex initialized to 1, and integer read count initialized to 0. So these are the variable that can be used in order to cater this problem or structures about the readers and the writers. So this is the structure of the writer process. So do, wait, read, write mutex. Writing is performed at this point, and then waiting for the signal for read and write mutex while true. So this is the process of writer or writing or update the data. So this one is the structure of the reader process. Okay, need to wait for the mutex, and then count the read. If the read count equal to 1, so wait, read write mutex, and then wait for the signal mutex. So this part reading is performed, so we can count the read. And then wait, mutex, read count decrease. Okay, subtract. So if read count equal to 0, so signal read write mutex, signal mutex while true. So first variation, no reader, keep waiting unless writer has permission to use the shared object. The second variation, once writer is ready, it's perform the write as soon as possible. So these are the variation, the first and the second. Okay, both may have starvation leading to even more variation. In on certain part, instead of only the first and the second variation, it can lead to more variation. So this problem can be solved on some system by kernel. Okay, we by kernel providing the reader writer lock. So we lock on certain part, so only can read and only can write. So this is readers and writer problem. Multiple user able to read, and only we also have certain user that allow to write. And then this is our library. So this is just the analogy of data inside of computer system. So database to be shared among the several concurrent process. I mentioned before, we have the data, and that data is accessible for multiple process. Some processes want only to read, and some other processes want to read and write. So several different version. We have first readers, writers problem, and second readers, writers problem. So these are the version: first reader writers and second readers writers. Refer to this variation. Okay, this is the shared resources, readers and writers. If they go one by one, then it will not have we don't face with the difficulties and the problem. But if they try to do that concurrently, just like you only have one book and you want to read the book, and your friend also want to read the book, and the other friend also want to read the book, so it might be a problem. Okay, this one we have the exclusive writer. So only when we allow the writer to do something on the shared data or shared resources, so the others need to do nothing. So that is basically about the reader and writer that lead to the synchronization problem on the data in our computer system. So the next part, the third issues, is about the dining philosophers problem. In this part, you need to imagine that you have at your dining table with your friends or your family, okay? And then you have the rice on the top of your table, a bowl, several bowl, and chopstick. Okay, you need to imagine that part. So based on this part, we can create the analogy of this problem, dining philosophers problem. So philosophers spend their life alternating thinking and eating. You're just like a student. So you are the philosophers. So you spend your life to think and to eat. They don't interact with their neighbors, occasionally try to pick up two chopsticks and one at a time to eat from a bowl. They need both to eat, then release both when done. This one is referred to the chopstick. Okay, you refer to this picture, we have a big bowl of rice, bowl, and when you want to use it, you need to use the two chopstick. So in the case of these five philosophers, we have the shared data is referred to the rice. This one is the shared data. So bowl of rice is the data set, and the semaphore is referred to the chopstick. So you can count, we only have 5 chopstick. So in array, we have a 5 array of chopstick. So initialize to 1. So this is the structure of the philosophers. I, a weight chopstick, a weight for chopstick, weight chopstick, 1 plus 1, remain with the 5, and then eat. When you have 2 chopsticks, then you can eat, otherwise you can't. And then get the signal, chopstick, and then after that, think. Eat, think, eat, think. So this is the analogy. You can eat, then you release it, then you can think. And then after that, you can eat again, and then you can think. So these are the structure. Okay, allow at most 4 philosophers to be sitting simultaneously at the table. Okay, this one is referred to the deadlock handling. I believe you also know what is the deadlock because we already discussed about the deadlock in the previous video. So allow a philosophers to pick up the forks only if both are available. This one, maybe we can use the analogy of the chopstick. So picking must be one in the critical section. So use a symmetric solution. An odd number philosopher pick up first the left chopstick and the right chopstick. Even number philosophers pick up the first and the right chopstick and then the left chopstick. So this is the what we call as a sudoku, like that, the algorithm. We have the philosophers, a chopstick, or forks. Yeah, the classical synchronization problem of the dining philosophers problem. We have 5 philosophers who only eat and think. So these are the philosophers who only eat and think. So each need to use 2 forks for eating. I think it's better we call as 2 chopstick for eating. So they only have 5 chopstick. We only have 5 chopstick on the table, but we have 5 philosophers. Illustrate the difficulty of allocation resources among the process without deadlock and starvation. Okay, these are the scenario. You can try to create the situation where the deadlock and starvation cannot be happen, cannot be occurs. With the 5 philosophers that only eat and think, and you only have 1 bowl of rice to be shared, and the resources you only have 5 chopsticks, but when you want to eat, you need to use 2 chopsticks. Okay, semaphore are a powerful tool for enforcing mutual exclusion and coordinate processes. Okay, this one is recalled back to the previous video on the semaphore. Okay, we have weights and we have the signal. So the weights and the function signal are scattered among the several processes. It's difficult to understand the effect. Usage must be correct in all processes. Mean the use of the weight and the signal must be correct. Otherwise, the process may be lead to the kelam-kabut situation. So one bad process can fail the entire collection of the process. That's why the usage must be correct for the whole process. This one is the real world application or situation of this classical problem on the synchronization. For producer and consumer, okay, you can goes for the web server architecture. So in the web server, its content trade and consumer or browser trade. Okay, server trade at the server, and then consumer or browser trade after server and client there. And then we also have streaming audio and video. Okay, network and display thread communication through a shared buffers. So this one is the real world situation that might happen when we talk about the synchronization in our computer system. The producer and the consumer. And then we have means that here when the consumer demand, so the producer need to produce. Only when the producer produce, then the consumer can use the product. Okay, something like that. And then for the readers and writers, the example is when we share a file on our disk. So the process of read and update the data on our disk, and as well as the database application. So if you learn about database, you also will meet about the term deadlock. How to ensure that the process of deadlock will not happen to your database, and how to ensure that the synchronization of the data in your database are maintained and well processed. Okay. When we talk about database, there are certain part when you change, right, then you need to commit. So the process must be in the synchronization. This is just like when we want to withdraw our money in our ATM, and at the same time there's someone that try to deposit certain amount in our account. So if the process do not meet the synchronization, do not have the synchronization, your amount balance in your account might be affected. That's why the synchronization is very important. And the third part is about the dining philosophers. Think, eat, and think. So cooperating processes that needs to share the limited resources. Okay. This one refer back to the analogies that we have 5 philosophers. We have a rice on the table, but when we want to eat, we need to use 2 chopsticks, but the resources are limited. So a set of process that require access to multiple resources at the same time. And this one we can refer to our printer. When you want to print multiple document using only one printer. And then online course scheduling, user account, course database, timetable, and classes. So this the real situation or real world application of this classical problem on the synchronization. So how we want to handle it, so is based on the structures and the algorithm that being shown before. So end of this part 2. So the next we go for the chapter 7, but your test only cover until the 6. So that's all for synchronization part 2. So basically you should know how important the synchronization in the computer system, what are the problems, and how to cater it. Okay? Thank you and assalamualaikum.